All right, welcome back to another online lecture for Calculus 1. This will be a continuation from our last video where we're learning about derivatives of inverse functions. In this video, this lecture particularly, we'll be addressing part 3, derivatives of inverse trig functions. So let's go ahead and get started. And we'll pick up where we left off on part 3, derivatives of inverse trig functions. So our starting place is to keep in mind there's 6 trig functions in total. Each of those trig functions has an inverse or opposite. So we have kind of 6 more derivative formulas to kind of learn. All right, our first place is just to recall some familiar notation. We use the f inverse, f to the -1 notation for inverse trig functions here, writing it as inverse sine, or to avoid confusion with a negative first power as an exponent, we can write this as arc sine. So we're going to use notations back and forth. You'll likely see them occurring in the homework questions both ways, sine inverse of x or arc sine of x. They mean the same thing. All right, and thinking back to what we did in the first video, when we were doing our review of inverse functions, we have this kind of conversion formula that allows you to convert on the left side from inverse trig form to trig form on the right. All right, now, one thing to keep in mind with inverse trig functions is trig functions by themselves are a little confusing for students. Inverse trig functions are usually even more confusing. Now, if you take a look at the right-hand side, sine of y equals x, remember what you plug in to trig functions. You plug angles into trig functions. You get as output numbers. So on that right side, sine of y equals x, y represents an angle, x represents a number. So when you take a look at the left side now, inverse sine of x, anytime you see an inverse trig function, that represents an angle of some sort. All right, you might last have used inverse trig functions in maybe some trigonometric word problems, given certain side lengths, determining the angle. So here we have a basic right triangle with side lengths 2 and 3. They are respectively the opposite and adjacent sides to that angle theta there for that right triangle. And if you were trying to figure out what the angle theta is for those side lengths, you can first start with basic SOHCAHTOA. Tangent of theta should be opposite over adjacent, and we get tangent of theta equals 2/3 here. Now to solve for theta, we use the inverse function, take inverse tangent of both sides. It cancels out on the left side, leaving you theta, and we get tangent inverse of 2/3 on the right. And to get an actual angle in degrees, you can use your calculator in degree mode to find that inverse tangent of 2/3. That angle is approximately 33.7 degrees. So that might have been how you last recall using inverse trig functions. What we're going to be interested in now is the calculus question. We're going to focus on just inverse sine first. If y is sine inverse of x, what is its derivative y prime? All right, and we're going to kind of take the same path to this answer like we did with finding the derivative of a logarithm. We're going to convert from inverse trig form to this implicit form, sine of y equals x, and then we'll apply implicit differentiation. All right, so from that right side, sine of y equals x, we're going to start by differentiating each side with respect to x. Sine is going to differentiate to cosine, but since there's a y in it, we multiply by y prime. So if we calculate those derivatives we get to here, notice the derivative of the right-hand side, x, differentiates to 1. And like before, we can easily solve for y prime by dividing. And we get the y prime here, our derivative, as 1 over cosine of y. Now here, we're kind of in the same predicament we were back with exponentials and logs. We want to convert this answer back entirely in terms of x. And this is a little bit tricky here because our starting equation kind of a few lines above was sine of y equals x. So we don't have a way to determine from that statement what cosine of y is. There's a number of ways you can convert back. One method is using a combination of trigonometric identities, but I find a lot of students forget some fundamental and basic trigonometric identities. So we're going to rely on an alternate approach to do the conversion, going to sine of y equals x, and thinking of that through the lens or view of basic SOHCAHTOA. Now for SOHCAHTOA, we have the trig function sine, cosine, or tangent equal to a fraction. On the right side, it was x, but you can think of that as the fraction x divided by 1. And with that, that expression, sine of y equals x over 1, we can make a simple right triangle. We'll label the angle in the lower left corner as y. And then relative to that angle y, sine being opposite over hypotenuse, we get the opposite side as x and the hypotenuse here as 1. All right, now in order to do the conversion for our y prime down there, we're going to need what cosine of y is. And to do that, we're going to need the third side length. So pause the video, give a quick calculation using the Pythagorean theorem to figure out that adjacent side that is missing in that right triangle. So we'll check back in maybe a minute. Welcome back. If you apply the Pythagorean theorem correctly and then solve for that unknown side, you should find that you get the square root of 1 minus x squared. And with those three sides determined, we can look at what cosine of y is. Recall from basic SOHCAHTOA, cosine is adjacent divided by hypotenuse. And if you plug in those sides there, the adjacent side is the square root of 1 minus x squared, and the hypotenuse is 1. And that fraction just simplifies just to square root of 1 minus x squared. Okay, so at this point, we've succeeded in our conversion. We've converted cosine of y in terms of x. You can plug that back into your derivative for y prime. And what we get for y prime, only in terms of x now, is 1 divided by the square root of 1 minus x squared. And this is our first of the 6 inverse trig functions derivatives. Okay, so that was the derivative of inverse sine. Let's go ahead and see if we can kind of go through that to see what the derivative of inverse tangent is before we kind of state all 6 inverse trig derivatives together. All right, so we're going to start by converting from inverse trig form to implicit form. Tangent of y equals x. We can differentiate both sides with respect to x, recalling that the derivative of tangent is secant squared. Since there's a y in it, we get secant squared of y through implicit differentiation, multiplying by y prime at the end. Like before, we can easily solve for y prime by dividing by secant squared. And you might recall the relationship between secant and cosine. They are reciprocals. If you plug in secant squared as 1 divided by cosine squared, that fraction within fractions will simplify to just cosine squared of y. All right, now we need to convert back this answer in terms of x. Going to our original implicit equation there, tangent of y equals x. We can rewrite this as tangent of y equals x over 1. We can label the opposite and adjacent sides for tangent. Remember, tangent is opposite over adjacent. And again, we can apply the Pythagorean theorem to figure out that hypotenuse, the remaining side. And if you do that, you should find that you get the square root of 1 plus x squared. Now what we want to convert back is cosine of y. And if we keep in mind, cosine is adjacent over hypotenuse, we get this. Cosine of y will be 1 divided by square root of 1 plus x squared. All right, if we plug that in, we get for y prime, the derivative of inverse tangent in terms of x This simplifies to just 1 divided by 1 plus x squared. Keep in mind, since you have cosine squared of y, you're squaring that square root expression above. Squaring the square root cancels out. All right, and we now have our second of all 6 inverse trig functions derivatives. Now, hopefully you get a sense for how this works. I encourage you to replicate this for all other 4 inverse trig functions derivatives, but we're just going to summarize what they all work out to before we get to some examples. All right, now I'm going to arrange the 6 inverse trig functions in the derivatives in a similar pattern to how we had the derivatives of the 6 trig functions. We're going to have sine, tangent, and secant on the left side from before, but now we have sine inverse, tangent inverse, and secant inverse. There's a similar pattern with negatives appearing in the other 3 on the right side. All right, so we did the first 2, the derivative of inverse sine and the derivative of inverse tangent. All right, I'll leave it just as maybe an exercise for you to try. The derivative of secant inverse works out to this: 1 divided by x times the square root of x squared minus 1. On homework questions, quizzes, exams, you don't have to go through kind of the work that we did here to find derivatives of inverse trig functions. You can just kind of memorize these as a starting place. Okay, now that's half 3 out of the 6 inverse trig functions and their derivatives. We have 3 more to go, but they fit a similar pattern to the derivatives of the basic 6 trig functions. The other 3 all get a negative in their derivatives, but now it's pretty much the negative of the related inverse trig function. Notice the derivatives of sine inverse and cosine inverse are very similar, just with a negative, and that pattern continues through cotangent inverse and tangent inverse, and cosecant inverse and secant inverse. All right, so just basically memorize all 6 of these. That's going to make homework problems, quiz, and exam questions go as efficiently and quick as possible. And also some things you'll be getting to maybe in Calculus 2 will build off of that. Now for Calc 2, all 6 aren't important, just sine inverse and tangent inverse for their derivatives. If you are moving on to Calculus 2, really try to understand these derivatives, particularly those 2, the derivatives of inverse sine and inverse tangent. Those are going to occur in a lot of places within your Calc 2 course. Now, before we get to some examples, I would suggest maybe copy these down into your notes just to refer to when we go through the examples. That way you don't have to pause the video and go back and forth. So maybe take a minute, write these down, refer to them from your textbook, and then we'll get to some examples. All right, so for example 4, continuing from video number 1, part 1 of the derivatives of inverse functions, here's our final example. We'll look at 2 parts. Both parts A and B are asking you to find the derivative for those functions, but notice now they involve inverse trig functions. So at this point, pause the video, give them a try. Think of using a combination maybe of chain rule and product rule for some of these, and check back in once you made an attempt at these. Welcome back. Let's start going through these final 2 examples. For this first one here, part A, be careful with notation. This is not sine inverse times e to the 2x. The notation here denotes composite functions. E to the 2x is plugged inside of inverse sine. So make sure you're comfortable with notation here. There's no multiplication, but one function plugged inside another. So we differentiate this, not using the product rule, since there's no multiplication, but we're going to apply the chain rule. So if we go through divide and conquer, our outer function here is inverse sine, and the inner function is e to the 2x. The derivative of f here, f prime, that's one of our new formulas, inverse sines derivative, the square root expression. And then for the derivative of g of x, that requires the chain rule. You might want to use the general exponential rule here. The derivative of the inside, 2x, is just 2. That's where that factor of 2 out front appears and comes from for g prime there. All right, we now have all of our pieces, but kind of plugging things back in gets a little trickier here. Be careful for the chain rule, g of x is plugged inside of f prime. And notice in that formula for f prime, there's an x but squared. Be careful to use parentheses. Inside those parentheses, we're plugging in e to the 2x. And then that quantity is still squared since f prime contains x squared in that denominator. Okay, from the chain rule, we get to here, f prime of g of x, and then times g prime. And if you simplify this, notice in that, that fraction with the square root in it, e to the 2x squared, when you have an outer and inner exponent, you multiply them. And if you multiply 2x by 2, you'll find that that multiplies out to an exponent of 4x. And we can combine that all as a simple fraction here, and we get this result for our y prime, our derivative. All right, let's move on to our last example, part B. This one is probably the trickiest within all the examples for these two videos. This one's going to involve the product rule, since we're multiplying there. And then it's also going to involve the chain rule, but with now our new formulas for derivatives of inverse trig functions. So this involves the product rule as well as the chain rule. All right, so we have our two factors there, f of x and g of x. The derivative of x is much simpler here, just 1. Differentiating g of x, tangent inverse of x squared, that requires the chain rule. And recall what we had as our new formula for the derivative of inverse tangent, 1 divided by x squared, but due to how the chain rule works, we get in that expression x squared squared. So take some time, make sure you can work that out and are comfortable with that, that the derivative of inverse tangent of x squared simplifies to 2x divided by 1 plus x to the 4th. All right, and if we combine our pieces here, we did the dividing, splitting into easy pieces. Now we can get our answer by conquering, putting the pieces back together. Our answer should take the form from the product rule, f prime times g plus f times g prime. And we have all of our pieces above. And if we plug it in, we get to this result, which can be cleaned up a little bit. We don't need the multiplication by 1. And I can move that factor of x right after the addition sign. I can move that factor of x into the numerator, turning that into 2x squared. All right, so that concludes the second part, our final video on derivatives of trig functions. Make sure to go back and refer to the first part to kind of thoroughly understand this part.